All right, so our motivation for this project was the purpose of this experiment was to see how the shape of the Play-Doh impacts the overall velocity in class. The reason we wanted to do this was we went over that problem with the paper and how when it drops flat and when it's crumbled up, even though it has the same mass, how the velocity changes, and that is why we wanted to do this experiment. And the main problem is although the mass and height are kept constant, the overall shape of the object may impact the velocity as seen in the lined paper example, which I just explained. The goal of the experiment is to investigate how the velocity is affected by the shape of the Play-Doh. And we know that an inelastic collision means that some of the energy is transferred out of the system so that the final kinetic energy is less than the initial kinetic energy, although momentum is kept constant. And for our research question, it is how are inelastic collisions impacted by the overall shape of the object? So this is our experimental design and setup. Basically, we had the Play-Doh that had a mass of 0.0735 kilograms that the person was holding at a height of 28 inches. The mass was kept constant, and same with the height. So these would be considered the independent variables. We used a meter stick to measure the height of the drop to keep this unit constant. And we shaped the Play-Doh into 4 different shapes to see how the velocity would be impacted. We had a round ball, a flat ball, a more round than flat ball, and a more flat than round ball. And the Play-Doh was released from the person's hand onto the ground outside of homes. And we saw that our results had a final velocity of the round ball had one of negative 3.54 times 10 to the negative first meters per second. The flat ball had a final velocity of negative 3.06 times 10 to the negative 1 meters per second, and more round than flat ball had a final velocity of negative 3.4 times 10 to the negative first, and then the more flat than round had a final velocity of negative 3.545 times 10 to the negative first. So as we can see, these velocities did differ a little bit, even though they did have the same mass and the same height. Some potential sources of error and inconsistencies between results in models. Our model is that the exact height could have been off due to just the position of the person's hand. This might not have been completely exact every time. Also, the angle that the ball is falling is going to differ every time because of the shape. So that also is an inconsistency that wasn't taken into account for. And also the fact that we modeled the shape of the object by hand, that could definitely cause some sources of error due to the fact the shapes were not like super exact due to the fact we did these by hand. And as I stated, the independent variable would be the height and the mass, and the dependent variable would be the velocity. After exporting our data into Excel, we were able to find the values of uncertainty for velocity for each shape. So the standard deviation of the round ball would have a value of uncertainty of 1.933. The standard deviation of the flat ball would have a standard deviation of 1.09. The standard deviation of the more round than flat ball would have a standard deviation of 1.919, and the standard deviation of the more flat than round ball would have a standard deviation of 1.21.
Okay, so in terms of physics models for our project, we used Newton's second law of motion, which is force equals mass times acceleration. And so in our experiment, the mass is the same, so it relies on acceleration to determine the net force in the system. And then we also use the law of energy conservation, which states that the total energy in the system is conserved, where the initial energy equals the final energy. And then we also use the momentum equation, where momentum equals mass times velocity. So in our experiment, we can determine how the shape of the Play-Doh affected the momentum or the object's momentum by using its final velocity. All right, in terms of data and calculations, we first tracked everything in Tracker, and then we put that data into Excel. And so you can see that for each shape of the Play-Doh, these are the position graphs, which highlight the average velocity. By looking at the slopes, you can see that the round ball has the greatest velocity and the flat ball has the smallest velocity. And then these are our velocity graphs, again, for each shape of the Play-Doh. This one was a little bit different than our position graphs. You can see that in the more flat than round graph. Our round ball, again, still had the greatest final velocity, and our flat ball had the smallest with a value of negative 3.06 times 10 to the negative 1. But we did see that the more flat than round ball had a greater final velocity, which was negative 3.45 times 10 to the negative first, compared to the more round than flat ball, which was negative 3.4 times 10 to the negative first. And this, again, kind of like how Sophie said, this could be from inconsistencies, either just with tracker, because we were having a few issues with that we had to do these calculations multiple times, or just inconsistency of height and shape of the Play-Doh itself. And then we also determined the final kinetic energy of each shape. So we used the equation 1/2 mv squared equals kinetic energy. So for the round ball, you can see that it had the greatest kinetic energy, greatest final kinetic energy. Oh, and it's important to note that the initial kinetic energy for all of these was 0 because it started not moving. And so round ball had the greatest, and again, the flat ball had the smallest kinetic energy.
Okay, so wait. Okay, so kind of just wrapping up, we saw that the round ball had a greater final velocity than the flat ball, and it also had a greater final kinetic energy than the flat ball. And so we see that the flattest object had that smallest final kinetic energy compared to all the other objects, which may provide evidence that more energy was lost internally due to some other thing like air resistance compared to the rounder ball or the rounder objects. And the data for the more round than flat and the more flat than round is not as concrete, because we saw that the final kinetic energy for the more flat than round actually ended up being greater than the more round than flat, which was kind of the opposite of what we were thinking might happen. So it was definitely a point of uncertainty within those two like middle shapes. So overall, we have provided some evidence that a round object will have a greater final velocity prior to the collision than a completely flat object, and thus it will have a greater final kinetic energy than that of the flat object because it loses less energy internally due to air resistance. Thus, we can hypothesize that object shape does impact the inelasticity of a collision, and this may have been due to the fact that flatter objects lose more energy to air resistance, leading to smaller final kinetic energies, as more energy is lost internally. So more research is needed to explore how object shape impacts collision inelasticity, as our results for the middle two objects were not as conclusive. And we can't conclude to what degree object shape impacts the inelasticity of a collision. So this is a point of further research. Again, sources of error, we molded the objects by hand, which isn't ideal, and there could have been some sources of like error using tracker and having to track the movement of the object as it fell. But yep, that was our experiment. Thank you very much.